Tech-ni-shn here again. Today we will be looking at the Minikits EME211 Notch filter and attenuator. Minikits in Australia does a number of excellent kits, and this is one of them. The picture shown on the screen is of the PCB assembled for the 9 MHz Notch filter and attenuator. In receivers, there may be off-air signals at the same frequency as the IF, and in this case it's 9 MHz. There is sometimes insufficient rejection by the mixer and bandpass low-pass filters, so a notch filter can be used to reduce signals even further into the noise. In addition, there's some manual attenuation to reduce antenna noise or to reduce the level of signals into the receiver. The board shown in front of you uses a parallel tuned circuit that is in series with the signal, and a series tuned circuit which is in shunt across the 50 ohm path. Also, there is two attenuators of 6 and 12 dB, and they can be switched in or out depending on the requirement. The Minikits site does show the testing that Minikits did on this board, and it is very good for the rejection of the 9 MHz. The addition of the attenuator is also shown in the testing. The equipment used is the same as what I've used before. I don't use all of the equipment on this test, but it is useful to have that shown. I will be using primarily the Siglent SSA 3021X spectrum analyzer with tracking generator. The image shown on the screen now is using the setup for looking at the the loss in this case. I'll need to amend the document. The output of the notch filter goes back into the spectrum analyzer input, and I'll look at the results of that. I'll also switch in the attenuator at different points and show what the response does with that. Also, we'll be looking at return loss and using the setup as you've seen before. The return loss at the 9 MHz is extremely low, as it's probably a very high impedance reflecting back into the return loss bridge. The testing will be after this information. Hello, this is the testing of the insertion loss of the notch filter. I've gone to a narrow span of 500 kHz across the screen so you can see the depth of the notch. It is approximately 60 to 70 dB at the null. I will now go to a wider span and show the notch. It looks shallower at the wider span, as the sweep is a fairly coarse sweep, so you don't see the depth of the notch. As I said previously, the depth of the notch is not as deep as on the narrow span, because the sweep is fairly coarse. I will now insert a 6 dB attenuator, and the insertion loss is approximately 6 dB, as you can see on marker 3. This is 12 dB, as you can see on marker 3, and both these together will be approximately 18 dB, as you can see on marker 3. I have the equipment set up to look at return loss. There is no attenuation in circuit. The return loss at 9 MHz is extremely low due to the high impedance being presented to the input circuit. The return loss at 7 megs is approximately 12 dB, and the return loss at 14 megs is approximately 22 dB. I'll now insert 6 dB, 12 dB and 18 dB attenuation, and you can see the return loss improve due to the effect of the attenuation. This is 6 dB attenuation, and since the signal goes into the attenuator and comes out again, the attenuation is approximately 12 dB. This is with 12 dB attenuation in, and you can see that the return loss is approximately 23 dB. This is with both attenuators in, which is 18 dB of attenuation, and one can see that the return loss is approximately 40 dB.